Okay, good afternoon. This is the LWIG working group session. Displayed as the note well, so please read this carefully. So can we, do we have a minutes taker and a Jabber scribe? Any offers? Etherpad, okay, thank you. And Jabber, can anyone do man Jabber? Jabber, anyone? Silence. Okay, thanks, Hannes. So here's there's a link to the meeting material and the Jabber room and the blue sheets that should be going around. And again, if you get up to the mic to speak, please speak clearly and state your name. Thank you. So here's the agenda. I don't know if do we need to do any agenda bashing on this? Anyone have any other items they want to talk about? Okay, hearing none. So I'll just quickly give a quick update on the document status. So the LWIG cellular document, so there's a working group last call issued. There was little response on the mailing list, but there were no objections, so I assume that's a tacit approval. And so therefore we'll advance the document. With the energy efficient draft, there's a presentation today from Carlos. Is he here? Yep, there you go. And I guess I think he asked at the end whether he thinks it's ready for working group last call. There's the IETF minimal, so Terra up issued this document, and because this has been around for a long time, I'd suggest this goes to working group last call immediately after this meeting, unless there's any objections to that. So I'll post that on the mailing list. There's a couple of expired documents. There's a LWIG co-app, which I think Matthias is just going to give a quick presentation on. Or no, he's not going to present on it, he's just going to make some discussion on this. And TLS minimal, again, I think this is kind of just a hangover from where we were in Honolulu, really. So I don't think there's been any change to that. No, Hannes is shaking his head. Okay, so the first presentation is from Carlos Gomez.
Thank you. Good afternoon. My name is Carlos Gomez, and I'm going to present an update on the draft entitled Energy Efficient Implementation of IETF Constraint Protocol Suite, also known as the Energy Efficient Draft. Okay, let's take a look at the status of the document. This draft was last updated around 3 weeks ago. This last version, which is -02, intends to incorporate the feedback collected during the last IETF meeting in Honolulu, in which there were several useful comments given by people, so thanks for this. The main additions in this new version can be found in sections 3 and 6, and also several minor changes have been done throughout the whole document. So let's take a look with a little bit of more detail on these changes. In section 3, which is the section which focuses on radio duty cycling techniques, there is a new subsection 3.3 entitled throughput. This is for completeness because, for instance, in this same section, there was section 3.2 focusing on the impact of radio duty cycling on latency and buffering. So we have added this section on throughput, acknowledging in the text that this is not typically a key concern in constrained node networks. However, it's still important in some services, such as over-the-air software updates, or also when sensors which are offline mostly have some short opportunity for transferring measurements which have been accumulated during this offline period. Also, we state that radio duty cycling leads to yet another trade-off. This time it's between energy consumption and throughput. Another change is new subsection 3.4 entitled Radio Interface Tuning. However, most of the text here is text which was previously in section 3.2 in the last draft version, and this change has been done mainly to achieve a better document organization, and also there is some additional sentence to make a more smooth transition to the next subsection. So this next subsection is 3.5, which corresponds to the old section 3.3. This is the section focusing on the power safe services available in example low power radios, and the main change in this section is in subsection 3.5.1, in which we have deleted the V in the title. In the title there used to be, well, it could read Power Safe Services in 802.11b. However, we have added some text on the Power Safe mode, which has been was actually defined in the very first version of the 802.11 standard, which is also important here. So now this subsection has a more generic form. Okay, another section with some changes is section 6, which focuses on application layer. Now there is some structure added to the document, in the sense that previously there were no subsections here. Now we have tried to organize a bit better the content with these three subsections: 6.1 entitled Energy Efficient Features in Co-op, 6.2 entitled Sleepy Node Support, and 6.3, which focuses on co-op timers. The content in subsection 6.1 and 6.3 is the same as in the previous draft version, and the changes are mostly in subsection 6.2, where we have added a reference to the published subscribed draft. Also, we mentioned the OMA lightweight M2M Q mode, and also we mentioned the 1M2M co-op binding with an application layer mechanism for sleepy nodes. So other changes applied to the document comprise the following. If you recall, there was section 7 focusing on cross-layer issues, which was almost empty, and in fact the consensus in Honolulu was to remove this section, so it has been removed in this last version. Nevertheless, there's still, we have incorporated a comment from Dominic, who mentioned that it could be useful, positive to have good interfaces between layers anyway. And other minor changes have been applied throughout the document, mainly clarifications, also editorial improvements, and a couple of new references which have been added. So after these changes, we believe that the document is mostly ready, so we would like to ask the chairs whether it is possible to issue a working group last call.
Okay. So I'd just like to ask the question to the room. Does the room think this document's ready for working group last call? First of all, who's actually read the document? Earlier version, okay. So, okay, questions?
Yeah, Dominic Barton. I read
Name,
the
please.
document.
Name?
Dominic Barton.
Dominic.
I read the document. I find it excellent. Lots of useful information. Very good work. I have two suggestions. One is for 15.4e, you describe the TSCH mechanism. I think, unless you have another opinion, just to be fair, DSME should be mentioned as well, if not described.
Okay.
I know that there's a 6-dish working group, there's no 6-dimish working group. So I don't know. If you have any opinion, does the industry care about DSME? If it doesn't, then fine, drop DSME, but I'm not sure. And the second point, what was the second point? Oh yes, you mentioned BTLE in the document as well. And as a co-author of a DAC-TULE draft, if time permits, I would love to be able to add a section on DAC-TULE as well, just to have a complete picture So I know, then I take the onus of providing text. We'll try to do that.
Okay.
But you know,
Okay.
I don't want to delay the document otherwise.
Okay, thank you very much.
Okay. Well, if that can be incorporated, quickly, then do you think it's worth incorporating those?
Sorry?
If that can be done quickly, do you think it's worth incorporating those as well before we?
Yes.
Okay.
I think can be done. Yes.
Okay. So if you can do that, Dominique, that'd be good. Thanks. Okay. So thank you very much. The next item is basically Matthias. Could you you've got 10 minutes to just talk about LWIG CoAP?
Yes, so actually there haven't been any changes since last meeting. The main problem I had back then already was that there was no feedback from the mailing list or from anyone else. My question here would be, who in this room has implemented CoAP at least once or half the time? Actually, quite a lot of people. It would be really nice if you would send a comment to the mailing list so I can come back to you, or even better, if you actually have input on what were the challenges. So where did you struggle? Where did you think you have a quite interesting solution to these problems, to actually integrate that, to have actually this implementation guidance we want to have in this document?
Okay.
So yeah, please do that, and from there we will then move on fast, I guess, because if there's nothing more to add, we should come to a conclusion here.
Okay, I'd suggest putting a request out on the mailing list and on the CoAP core mailing list as well. So, because I imagine a lot of people who have implemented probably follow core more than LWIG. So. Okay, so Hannes, you're up next.
Okay. I wanted to talk a little bit about performance analysis I did with a co-worker of mine, Manuel. And okay, next slide. So a little bit about the motivation of why I had been actually working on this was the in the meanwhile expired LWIG document initially contained guidance and also performance figures. So if you look up, try to find the expired version, that's what you're going to find in there. But in the meanwhile, after the work was started, the DICE group was formed, and there we had the DTLS, TLS profile document work going on there. And most of the guidance actually moved ultimately over there and was expanded later on, and the document passed working group last call already. And what it does, the DICE document, as you know, looks at different credential types and also looks at different communication patterns and looks at different extensions. And so a question that comes up is quite often is like, what does it really cost? And even during this week, I've heard a couple of times presenters claiming that we can't do public key crypto on IoT devices and so on. And of course, the answer to that, or what IoT devices can do and cannot do, is more complicated. And even the former presenter here about energy efficiency, like obviously this is not a yes or no question, but rather a question that has a more complex answer. And in order to provide better performance data for the TLS minimum document to actually make an informed decision about which features you should actually be looking into, I was doing this performance analysis. Okay, to actually enhance what is already in there, and have just better data. Okay. And that's what I'm going to talk to you about the status of that investigation. And ultimately, I hope that some of you can help me doing that work. So data we would like to have is, we would like to know what is the code size. So typically, code will end up in Flash, and how much code size do the different extensions actually need. The message size and the communication overhead is important to some of you, specifically if you use some of the low power radio technologies who have a very small MTU size. Got a lot of extension work going into that to reduce the size of the messages overall. CPU performance is important, energy consumption, referring back to the earlier talk, and also the usage of RAM. So actually quite a bit of data, and in this talk I focus on a few of those. Unfortunately, you don't have data for all of this yet. And as said, most engineers and product designers they want to have a rough estimate on what they can expect to actually choose the right platform rather than trying everything out themselves, which is a very time-consuming process. Just telling them use TLS and some of the extensions is not enough, I believe. So as said, there is already something in this TLS minimal document, namely we have code size of various basic building blocks, cryptographic functions and so on, ASM1 libraries, etc. But only from one single stack. So we ideally want to have data from different implementations, so we have a little bit more representative coverage. There's memory information in there, but unfortunately only for the pre-shared secret credential version. Nothing for the elliptic curve cipher suites that we also recommend in the profile document. And then for the communication overhead, there's only very high-level information there, mostly focusing on the record layer. Okay. So what we did is we've looked at in this specific case on asymmetric crypto, because it's obviously very demanding. There's a little bit of data on the symmetric crypto in there, but as you will see, that's not a problem at all. We looked at a specific processor family and ARM processors, and maybe some of you have time to look at other processors. And I know that some of you are working on other platforms, and so that would be good to have additional material. And so in the next couple of slides, I'm going to explain you, give you the background of the measurements and what assumptions are made, what boards and processors are used, and then talk about the actual performance data. And so that the material in the slide set should give you enough information to actually redo the test on your own to verify them. Okay. So the focus was, my focus was on raw crypto at this point in time, not the protocol exchanges, although I will sort of talk about, at the end of the presentation, talk about the relevance for the TLS exchange as well. I focused on ECC rather than RSA simply because that's what we recommend in a profile document. We don't recommend ECC use, so I didn't cover that. And specifically, what I was interested in is the performance of the different ECC curves, since this is an ongoing discussion in the TLS working group and also in the CFRG, which just met before this. So I covered the classical curves and also did some preliminary work on the curve that Dan Bernstein proposed, curve 25519. And particularly focused on runtime performance rather than energy consumption or code size. There's a little bit of RAM usage in there, but it's not in fully complete data, as you will see in a second. I didn't use any hardware acceleration to sort of mess up the data. I used open source code, namely I used the BOLA-SSL stack, which has been renamed to embed TLS stack, so that's so you can actually do the analysis yourself as well. The only caveat, the curve 25519 test code is actually not, the one that I use for testing is not yet available publicly because it's still in work in progress, as you will see later. Unfortunately, none of the boards that I have used has a hardware-based random number generator, which doesn't impact the performance numbers, but for real-world deployment, that wouldn't be such a great idea. So keep that in mind.
Hi, Hans. Kerry Lynn. Just a question on this, because you raised it in the plenary as well, and I'm just wondering if this is an area where we could do some further development. I'm just wondering, can people who are versed in security maybe school us a little bit on what constitutes a good source of entropy, and is there a very cheap solution that perhaps could be, maybe you're measuring thermal noise or something and just attach it to a GPIO pin? What's the most cost-effective way to do this? You don't have to answer now, but I'm just thinking that if this is going to be an ongoing problem, maybe it's one that we should look at.
That's a good point. So there's this IETF RFC that provides some information about that, but many of the recommendations or descriptions in there focus more on systems that have already some hardware components in there that can be used. So it might be good to actually invite someone to just give a talk to us and to inform us a little bit. Ideally, what you want to have is a microprocessor that has already a random number generator on board, and so you don't need to worry about that. And those exist. They just didn't happen to be on the boards that I have.
Yeah, maybe I can give part of an answer to that. It's pretty easy to measure thermal noise in a resistance or diode junction using an A to D converter. You need to have some gain, so if you have an operational amplifier around your microcontroller, you can use your ADC to measure noise, and that's a very good random number generator. You just need to be careful that you don't inject electronic noise from the power supply into your thermal noise, because then you will get correlation with the software activity of the node. So there's a little bit of decoupling of the electronic circuitry to be done.
So
but
I hear
this works.
A small hands-on workshop next the next IETF.
Yeah, I'd love to
solder things together real quick. Sounds like a nice idea. Okay.
Thanks.
So what I did, so obviously I have to use a platform, I have to use some processors, and so the different ARM processors, as you may know. So there's a Cortex-A series, which you find in your mobile phone, tablet, and your home router. Those I haven't used. They have high performance. They would have no problem at all with any of the crypto that you see. You would just love it. So I used the Cortex-M processors, which you find on many IoT devices if you look at the teardowns. And I looked at the ones that are, you see indicated here from M0, M0 plus, M0, M3, M4. I didn't use the M7 because I don't think it's actually available in silicon yet. The difference between them is, as indicated, so the trade-offs in terms of energy efficiency, cost, and feature set. So the ones that are M4s, they have floating point units and typically have more better CPU power and so on. So you will see that the impact in the data. So it's, all of them are 32-bit RISC processors.
It's probably worth mentioning ECC on the M7 doesn't mean elliptic curve, does it?
Yeah, that's a good point. Yeah.
So,
ECC doesn't mean elliptic curve. Okay. And of course, I didn't use just the raw processors, but instead bought some demo boards. I have some with me, so you can actually look at them. The nice thing about them is that normally for experiments, you already have all the pins there, so you need sensors on these boards and so on, so you can actually readily use them rather than building your own system. So as said previously, I have basically the full range of coverage, and I try to also have different boards with different CPU speed, so that there's a little bit of difference. I noticed that with my test program, if and as I explain later, if you don't have enough RAM, then you will not be able to use some of the optimizations, and then you are in an unfortunate state. We'll talk about that later. Okay, so what curves did I look into? And those are the curves that you may see also being discussed in a transport layer security working group. Specifically the NIST curves, which are very popular with different key sizes. So they have these funny names, and the number indicates the key length. So we're talking about key lengths in a second. The second type of curves I looked into the Koblitz curves, followed by the German brain pool curves, which are also standardized as an IETF RFC. And as I said, curve 25519, which is a more recent one, currently under discussion, and standardization efforts are ongoing. So we'll see those. From a recommendation point of view, COAP recommends the NIST curve 256 R1.
Sorry, Carrie Lynn again. Are these all unencumbered by IPR? Are any of them unencumbered by IPR?
That's a difficult question.
That is a question that nobody in this room can answer.
Yeah,
exactly.
However, there is an RFC 6090, which for some of these curves actually shows that they can be constructed from information that was available before the year 1994. So if you know about patent lifetimes, that if you are not a lawyer, this should give you some assurance. If you are a lawyer, you know that law is a little bit more complicated. Anyway, so that's one of the reasons, I think, why many people were quite comfortable with the mandatory to implement choices for COAP, which is P256 alias SECTI 256 R1.
Definitely. Yeah. Okay. Yeah, the note at the end, the FIPS related specification also gives them sometimes gives them a different names. So you see P and then followed by the key length P256. So depending on which document you read, you need to figure out what it maps to. So the Koblitz curves are easy to recognize because they have the K at the end after the number versus the R in case of the NIST curves. So I'm talking also about a few optimizations. Those are the first optimization, and then you see the references here for the details. They are already described, in case of the NIST optimization, they're already described in the NIST specification itself. So that's obviously an obvious thing to do. And what this specifically does, and this is actually, if you look at the elliptic curves, some of them are specially constructed, and the primes are specially constructed in such a way that it makes the point multiplication, the scalar multiplication faster. And that's why you see a difference between the performance of all these different curves. And so you need to look at, if you want to know more about this optimization, you go and click the links. So NIST optimization basically uses the structure, the special structure of the prime. The fixed point optimization pre-computes points because it uses a more efficient way of doing the multiplication and then the reduction. So naively what you would do is, like in general, like you multiply numbers and you have something like, let's say, number times x, and then you would basically go and multiply that point again and again and again, and then at the end you would reduce it back to the field you're using. But you can do better than that methodology, and there are different techniques suggested for that. And the one that I'm using here is called fixed point optimization. It's also implemented And some other people use more advanced techniques like the Montgomery ladder you may have heard in other working groups. And then finally, there's a runtime technique called a windowing effect. So the fixed point optimization can be done upfront, basically upfront if you know what. So it depends on the exchange, but in many cases it can be done upfront. And the window technique is also for efficient exponentiation, but it's a runtime technique. It doesn't offer such a tremendous performance benefit. And those are the parameters. So the window technique, I list them as a W, and the values are from 2 to 7, sort of. And the other ones, the NIST optimization, fixed point optimization, is either enabled or disabled. And you will see the impact of doing that. Okay, next one. So I looked into so the cipher suites that are standardized, that are also recommended. They are using Diffie-Hellman exchange, ephemeral Diffie-Hellman exchange, ECDHE, and of course the signature mechanism, ECDSA. And so if you look at that, the elliptic curve digital signature algorithm, which is sort of the elliptic curve variant of the DSA, or sometimes called DSS, and you will find it in this cipher suite that the one that is shown here in the second bullet may be familiar to you, because that's the one recommended also in co-op, and consequently also in the DTLS profile document. That issue came up just at the CFRG meeting. If you use the ECDSA signature mechanism, it has somewhat a poor randomness property. So it actually, the implementation uses in a randomized hashing technique, which is described in this RFC 6979, which prevents that you leak your private key if you use the same random number for the construction. So it's just a way how this digital signature algorithm works, because it's based on El-Gamal, and it's just different than what you know from the RSA case, in case you haven't looked at it. Co-op always recommends for the elliptic curve variants, or for the public key variants, to use the Diffie-Hellman exchange along with it, and particularly the ephemeral Diffie-Hellman exchange. And so I included that as well, because it obviously contributes to the overall performance and complexity of the whole thing. Okay. And this is an expansion of the slide I've shown during the plenary on the key lens. So needless to say that there's a trade-off between performance and security here. And so you see, you need to pick the right key size for the symmetric algorithms, but as well as for the ECC or ECDSA. And those values sort of the mapping from symmetric key performance to these asymmetric algorithms is basically taken from RFC 4492. So you need to make sure that the right things, that the things match up. And so if you look at the recommendation that the Utah document, the TLS-BCP recommends, then we are at around 230 something bits for ECC. Depending on which other recommendation you look, it's a little bit higher, sometimes a little bit lower. But just to give you a rough guess, so that's what you see. So I didn't do performance tests for key lengths which are far below what anyone recommends. Even though it would be great from a performance point of view. Some people do that. They show you smart card performance with completely ridiculous key sizes, and you wonder, oh, it works well. But the security is just complete crap. Okay. So as a summary, before I show you some of the numbers, so
can I just quickly add to that? So when we did the recommendations for actually the mandatory to implement decision for CoAP, we also looked at the expected lifetime of Internet of Things devices and assume these have a longer lifetime than your garden variety IT system. So we went to the conservative side there and went to 256 plus.
That's a good point to note that obviously, with the key size, you need to take the lifetime of the key into account. For certain cases, when you have a protocol that mints ephemeral keys, then it may be possible to actually use a shorter lifetime if they use it more as almost as a session key semantics, which is not so much applicable to the TLS exchange, but maybe applicable to some of the work that we currently do in A. So that's probably something to keep in mind as well. It's good to know. Go ahead.
Peter van Stok, a small question. Is this true, the conclusions over all processors?
Say that again?
Are these conclusions true over all processors?
Those here?
Yeah.
For all of the processors, I have tested. Yeah. Yeah. So the ECDSA signature is much faster than the verify operation. I think this is true even in general, just because of the way how the signature operation works. I think it's the other way around in RSA, if I remember correctly. So you need to actually be careful what you compare, because RSA can actually be faster computationally if you just look at the write operations. Of course, from a key size point of view, what you transmit over the wire, ECC will have an advantage, as you have seen on the previous slide. If you go back, and that's actually why the recommendation is to use ECC, because of the shorter key length, not so much because of the performance. Because if you compare, let's say, 112, you have 233 bits key size for ECC, but you need to use 2048 bits of RSA keys, for example. That's what this table from this RFC that I mentioned showed. Okay. The brainpool curves are much slower. They're slower than all of the other curves. So if you want to get performance out of your IET device, that's probably not a good approach to use those. They have some benefits, because they are the reason why they are slower is because they don't use specially crafted curves and primes, but they instead generate them randomly, which of course then you can't use a special structure because it's randomly chosen. So that's a downside. But those are used, for example, in smart grid deployments in Germany. So those will have, if you have a regulatory mandate to use that specific curve, then you have to live with it. The performance based on the bit length of the curves is obviously not linear, and so if you go beyond 256, because you have maybe a very long lifetime of your IET device, you need to crank up pretty massively, as you will see. The ECDH and the ECDHE is only there's only a minor difference, but since we are not using ECDH but only the ephemeral version, that doesn't matter that much. The CPU speed obviously has an impact, and the difference between the Cortex M0 and Cortex M0 Plus and M3, M4 is also that you have a couple of more instructions in the better processors that help speed up the performance computation.
A question about, you said that the NIST curves has also the property that it's very easy to implement it incorrectly, so they actually leak out information based on the timings. So is the implementations you are using here, are they constant time implementations?
Good question. So the implementation here, it takes into account timing side-channel attacks. All of the code is constant time. Good point. I forgot to mention that. What hasn't been, well, the aspect that hasn't gotten a lot of attention is other types of side-channel attacks. So that's something to look into, but timing side-channel attacks have been taken care of. Okay. Yeah. And as I will show, like symmetric key cryptography is not a problem at all. Okay. Let me skip that slide and go to the numbers. So I start with the M3, M4, which have a better performance. I hope you can see it. Otherwise, you need to click on the web page. So here I have NIST curves and Koblitz curves with a device. It's an ECDSH signature operation, so the faster operation, and with a device with an NXP LPC 1768. All of the optimizations that I showed previously enabled to the maximum. So what happens then is that operation takes, and those are milliseconds, if you can see that. So for example, for P192, the NIST curve, we're talking about, for the signature operation, 66 milliseconds. If we look at 256 key size, we're talking about 122 milliseconds here. The Koblitz curves are roughly, or about the same degree. So it's not a huge difference on this. So that's and I should have memorized on how fast that process is. But it's a faster one. But it's an M3. So those are roughly the numbers if you do the signature computation. So we're not talking about seconds here also. So that's, I would say, pretty fast. If you compare the signature to the verification operation, as I mentioned previously, signature is faster than verify, then you get something like this. If you, for the B192, you have, for the verification operation, you have 251 milliseconds versus the 66 we had before. So it is an order different. So if you have the chance to design your overall system, so obviously you want to minimize the verification operation on the IoT device and try to do the signature operation if that's possible. But we'll look later at what that means for TLS. And for the P256 curve, we have previously had for the signature of 122 milliseconds, and now we are talking about 458. So 450 milliseconds is of course something.
The slide should say signature there as well, right?
Yeah. That's there's a copy.
This is signature.
That's true. That's true.
That's verifying.
Copy and paste flow.
Yeah, that should be a signature.
That's great. I need to fix that. Okay. So you see sort of the absolute values and sort of what you can expect, and then obviously, of course, if you look at if you crank up the key size, then to 221, then we are already in a almost 1.5 seconds for the verification operation, which is quite a bit. Okay. Next one. And something on the brain pool curves. So this is the signature operation, the faster one. If you compare that, this is the 256 curve, and if you compare that, the 122 that we've seen previously against the brain pool curve with 674, that gives you an indication that obviously it's already for the signature operation is much slower. Okay. And then for the verification operation, more than almost 3 seconds. That's quite tells you something. And then for 512, like more than 10 seconds, it's massive. So it's for those type of processors probably, unless you have a lot of time, not really a useful thing. So,
that was also the point where we actually ran into problems with the GTLS and its default timers and so on. So yeah. It simply doesn't work if the other DTLS implementation doesn't know that you are very slow.
Yeah. So better avoid that. So as I said, the window parameter is one of those optimizations that helps to improve the performance. It's the one that has the least impact. But already with the signature operation, and I turned off or shranked it to the minimum window size, then you see the differences here from 66 milliseconds to 127. So it's already has some impact if you disable those for whatever reason. If the NIST performance optimization, however, is that's a completely different story. So here we compare. So those are different processors now. Also from the same M3, M4 category, but as you see in the top, this is actually the ECDH. This is the Diffie-Hellman handshake now. Here on the left-hand side, you see the optimization disabled. On the right-hand side, you see it enabled. Only the NIST optimization enabled. All the other optimization, the other two disabled. And you see the difference. For example, if you pick the B192 curve on the right-hand side, 638 milliseconds for the Diffie-Hellman handshake versus almost 6 seconds if you disable it. So obviously enabling this, using the special structure. So if you already use the NIST curve, then you better utilize the special structure of that curve rather than disabling that sort of optimization, which the standard would allow, but the performance impact will be clearly visible. So those are now for the low-end processes. And there, the story is a little more complicated. So here I disabled all the optimizations, basically making it as slow as possible, and the Diffie-Hellman exchange, ephemeral Diffie-Hellman exchange. So already, if I do that, already for B92, I have more than 5 seconds runtime for that, for the Diffie-Hellman exchange. Obviously not a great thing. Next slide. So this is the chip I'm using is a KL25 set. That's a Freescale processor, or a Freescale manufactured processor, and it uses the Cortex M0. We can go back to the original slide. This is the NIST curve B192 on this one, the smallest NIST curve. I didn't stop looking at the brain pool curves because it wasn't so beneficial. But you see, like here it gets a little tricky. If you go to the next slide. This is the signature and verify operations, and also for the same processor, like signature operation more than 2 seconds, verify operation for this 192 curve, verify operation more than 5 seconds. So it's takes a little bit of time. Yeah. Thanks. If I enable, however, all the optimizations, of course it gets better. So here's the handshake performance, and everything enabled, all optimizations. So if you look at the again at the B192 curve, then we are at about 800 milliseconds. So that's much better. It's still much slower than M3, M4 that we've looked into previously, but gets into a range that is more acceptable. And you can look at the detailed values afterwards. If for the ECDS, so the performance of the Diffie-Hellman is roughly similar to the performance of the verify operation, the signature verification operation. Of course, the sign operation is much better here for the B192, 225 milliseconds. So that's pretty good with all the performance enabled, and 845 for the corresponding verify operation, so almost four times the cost of the verify compared to the signature operation. Okay. So the CPU obviously has impact. So if you compare a faster M3 with a slower M3, 96 megahertz versus 32 megahertz, you see some impact. So it's not earth-shaking compared to some of the optimizations, but the difference here would be so I used the B192 as you see in the black box in the middle for the Diffie-Hellman exchange. We're talking about 280 milliseconds versus 230 milliseconds. Different, but not so dramatic compared to the other aspects. Okay.
Do you have an explanation for that? I mean, one would expect that this scales with a factor of 3.
What
are those algorithms memory intensive? Do you actually hit the memory bandwidth as opposed to the processor
actually,
cycle?
I have, that will be the reason. I have the memory data in a few slides. Yeah. So that may slow things down. Okay. And so here you see sort of a comparison among the different boards. And you see most of them, so those are M3 and M4. So if you, so of course, if you increase the key length, then of course it messes up the statistics. But if you just look at the first 3 bars for each processor, then there is a difference, but it's not so dramatic, and all of them have a fairly good performance.
Yeah, I think it's good to do this for a number of curves, but for curve, of course, the yellow bar is the one you want to look at.
It's probably the one we want, but I guess I think that's what we recommend. Yeah.
It's mandatory to implement.
Yeah. And if you look at the first one, the third one is 72 megahertz, 84 megahertz. It's a pretty reasonable performance, like under 200 milliseconds, with the optimizations enabled. Okay. And the curve 25519. So I looked into that one as well, and so here on the far left, there's this Cortex M0 with 48 megahertz called KL46Z, and there are 3 different performance or 3 different data I collected for 3 different implementations. The first column, the biggest one, is our implementation, non-optimized, for the elliptic curve Diffie-Hellman, and it was roughly 1.5 seconds for the curve, for that Dan Bernstein curve. If you, however, compare sort of the optimized version from Google, which we also ran on those processors, but haven't optimized for ARM processors, we just basically took the code that they optimized for the desktop and server environment and dumped it on the ARM platform. That has 550 milliseconds, so it's obviously a completely different scale. And to have the comparison with what I had shown previously, to compare this with the NIST B256 version that I had shown a few slides ago, that has 1,145 milliseconds. So if you compare that, so at the moment, sort of the curve 25519 implementation we have is actually slower than the NIST curve optimization. But the reason for that is because the code doesn't take, the big number implementation doesn't take into account the special structure of that curve, and that makes all these curves different. So that obviously doesn't help. So if you have an unoptimized version, then these new curves don't get you anywhere. However, if you optimize it, even if you don't optimize it for that target platform, for the right target platform, that already makes a huge difference. So it's twice as fast, which is good. And if you look on the picture of the LPC 7068, which is the M3, you see that the Google implementation on our platform has 90 for the Diffie-Hellman exchange has 94 milliseconds, which is actually pretty good.
So about 2 minutes left. About 2-3 minutes left.
Okay. So, and what is also nice about that new curve that is being considered is it has a very low RAM footprint. That's pretty good.
The 25519 numbers are actually the reason why we have proposed to have a PSK plus forward security.
Okay.
So there's a document, I don't know if it's actually expired or not, but we will revive it because it's really useful to have a PSK plus forward security for those applications where you actually want to use a PSK.
I think in general, once it's standardized, it will definitely be very useful. So this is only the Diffie-Hellman version because the work on the signature version is still ongoing. So the progress is a little bit different. There is, however, if you go into assembly optimizations, there's one other library that I looked into, the micro-ECC library, and that has also the code for the NIST curves. And you can see it's unlike the code, the Bola SSL code has no ARM assembly optimizations in there. And it turns out that you can actually, if you by hand craft the code, normally you would think the compiler is much better at producing optimized code, but in fact in this specific case it isn't. So if you look at the numbers, there's a huge difference between sort of the runtime of the numbers that I showed and what micro-ECC provides. So it's a factor 2 or 3 with those ARM optimizations, ARM assembly optimizations. So there's still, even if you just take the ordinary NIST curves and then do the assembly instruction optimization, you will still get out a factor of 2 or 3. And if you then switch to Dan Bernstein's curve and then optimize that further, I think there's good potential.
Randy Turner, I was curious what compiler you used for this to generate the code.
Say again?
What compiler did you use to generate the code?
I think we use
It's ARMCC 6 or something.
Yeah.
So the compiler that ARM provides.
Yeah.
Okay. All right. Thanks.
So we're just about out of time. Do you want to quickly?
Okay, I will answer very quickly. So we also looked at a memory consumption. We only measured the heap and not the stack, but the heap is where the memory comes in. The heap is where we have most of the memory consumption rather than the stack because of the way how the program is written. So if, the floating point, the fixed point optimization consumes a little bit of RAM. Here is the fixed point optimization is disabled, but as you can see, these elliptic curves of computations, they require RAM, at least certainly with the implementation that we have. And so depending on, of course, they depend on the size of the curve, but we're talking about for 256, for the 256 curve, 2 kilobytes for additional RAM that you need when you run those algorithms. Go to the next slide. If you enable the floating point optimization, then it obviously increases because the whole idea is that you cache points. And so we are talking about for the 256, we're doubling the RAM usage. And for curves with a high, with a long bit length, like it gets even over 14 kilobytes for the 521 bit curve. So the summary here is, if you want the optimizations, there's a trade-off with the RAM usage. So you obviously pay a price here, but I think that the benefit of enabling those optimizations pay off because you obviously get. So here, this figure shows on the heap usage in bytes compared to enabling the optimizations and disabling it. So there's obviously some difference, but on the next slide, the performance benefit that you gain is basically and the summary is, if you increase 50% of the RAM usage, you actually get an increased performance by a factor of 8 or more. So I would say go for the performance in this case. And then I'm applying the results to it. So those are the individual operations, but of course when you look at the TLS exchange, there's not only one, at least the cipher suites that we have chosen. So what you need is a couple of things, and so you need to add up the numbers to actually get the whole thing, ignoring sort of hash computations or the round trip delay as well, or maybe other things. So you would have to add for the ordinary exchange for the ECC cipher suite, the ECDSA verification, the ECDHH computation, and then ECDSA signature. So you have to add those up, and what you then get, for example, here I added the numbers up based on the LPC 7068 with the curve B224, so in between the ones, and you accomplish something like 700 something milliseconds. And of course, you may need to add a few additional signature verifications if you actually use the sort of the public key infrastructure. So this doesn't apply to the raw public key mode, but it applies to what is called the certificate mode in the specification. Needless to say. One quick word about symmetric key cryptography, because I said it's super fast. I skipped that slide. It's just an introductory of what that means. So if you look at here, I have this M0, sort of the really slow processor, and again milliseconds here. So if you look at the SHA-256, 2.2 milliseconds for 1024-bit hash over 1024-bit value, 2.2 milliseconds. Was a bit. Go back to the slide. One slide back.
Bytes.
Yeah. 120
bytes.
Okay. And the same for RSA. I used the same value. Okay. One forward. And for example, AES CCM 128, the same length, 5.8 milliseconds. So obviously, like symmetric cryptography, you don't need the hardware acceleration. No problem. Hardware acceleration or the hardware, AES and hardware may provide you other benefits in terms of side channel assistance, but from performance point of view, not an issue. Next one, faster processor. Obviously, like the M3, AES CCM 128, 1.7 milliseconds. It's obvious, not something to worry about. My conclusion slide. So needless to say that the ECC crypto needs some time, and we have chosen intentionally to also include that as those are the recommended cipher suites, and I had chosen the one that has a Diffie-Hellman exchange there as well, an ephemeral. So what the exact value is that one needs to worry about depends really on the actual application, because the good thing about DLS is it does the heavy lifting at the beginning, and then it establishes the session keys, and it may at some time in the future may need to refresh keys, but then in the meanwhile, in the time in between, you work with the symmetric keys, which are obviously super fast. What the exact performance is depends on, as you've seen, on a number of different factors, and so it's not a simple answer, but someone who works on a specific application has to then think about, like, what's the acceptable delay for the user when they set it up. Like, is this the setup that we do when the user unpacks the device and pushes the button and it talks to some server, where maybe a longer interaction delay may be acceptable, or are we talking about something where there's a real-time interaction needed, like whatever, and then obviously like half a second counts. Okay. So in terms of next step, so we obviously have seen that in one of the introductory slides that I there's some other data that I would like to collect, particularly on energy efficiency, which I haven't done yet, and verify some of the other data and do more on the new curves that the CFRG is looking into. So doing all that stuff is quite time consuming, as you can imagine, because I basically need to compile a code, download the firmware image, run the whole thing, and then of course I need to run the test for a longer period of time. So, and I need to manually do that, and that takes time. So if someone is interested to also look into that, that would be great. I would like, at the end, I would like to put some of the conclusions of this into the LWIG TLS minimum document with reference to what we did in the profile document to give developers and product designers some additional ideas what they get out of some of the optimizations.
Okay, thanks, Hannes. I would say we are 10 minutes over, but I wanted to get through this because it's very interesting. So go for it, Robbie.
All right, Robbie Simpson. Just a quick question. I was surprised to see that the performance for GCM was better than CCM, and I think the reason that most of the lightweight world is centered around CCM is simply because it's in hardware so often. Did you get any numbers on RAM or code usage if you don't use hardware acceleration for GCM versus CCM?
I didn't look into that because the focus was more on the heavy asymmetric crypto, but I could definitely look into that. I haven't also looked at some of the Cha-Cha and these type of algorithms that other people propose. They claim it's much better. Probably worthwhile to do that as well. That would indeed be useful. Yeah.
My thinking there is that GCM is the MTI suite for a lot of other protocols, so it'd be interesting to do the comparison.
Yeah.
Thanks. Very nice, by the way.
Okay, thanks a lot. So as I said, we are actually 10 minutes over, so we'll probably have to cut it off there. But thanks for your attendance.
So if you're interested to help or do some other tests, please let me know. Would be really happy. And I know some of you are working on code, so it would be good to have more data from different processors, different stacks, and so on. Thank you.
And has everyone signed the blue sheets? Where are they? Somewhere. Yeah, there's enough break and then it's cookie time.